Today we speak a little bit about MnSi, which is a non-centrosymmetric system. So why it is interesting? So let's write a generalized Hamiltonian for exchange interaction. So what is this? So these are the spins, and what is that? This is a tensor, which will depend on the position of the spin I and the spin j. And a tensor, whatever it is, you can always divide it into isotropic part that I will write this way here. So you take the trace, divide by 3. Anisotropic antisymmetric part that we can write this way, and anisotropic and symmetric part that we can write this way. So now you take that, put that in this Hamiltonian, and you obtain this Hamiltonian here. So now, what are all the terms? So the first term is what we know, the isotropic exchange interaction, so the Heisenberg term. The last term is an anisotropic term which is symmetric. It can be due to super exchange, double exchange, whatever. And what we have in the middle is the Dzerjinski-Moria interaction, antisymmetric. So normally we don't write it this way, but you can always write an antisymmetric matrix, like this guy here, as a function of a vector here. And here we have the Levi-Civita symbols. So LMN stands for X, Y, Z. If they are not all different, this guy will be 0. If there is an even permutation, X, Y, Z is 1. Odd permutation, this is -1. So now you can convince yourself in 2 or 3 lines that if you use that, you can rewrite this term as the Dzerjinski-Moria term that we know. Okay. Sorry. Yeah. Okay. So if I take now, sorry. So if I go to the Dzerjinski-Moria term, so what it will tend to do? It will tend to tilt the moment in the ground state. So if I write the free energy density, I can write it this way, for example, where here we have the magnetic stiffness. So the A is somehow proportional to J, the change that we had. And here we have the Dzerjinski-Moria energy. And depending on the ratio of D here, there is a D coming here, and A, we can have at low temperature a ferromagnetic state, because you would pay too much energy to tilt. And if you increase the D, you gain more energy here than you lose here, and you have helical state. Okay? So this is the Dzerjinski-Moria energy, if we want. So if it is centrosymmetric, normally this guy is 0. If it is a non-centrosymmetric system, so it's possible that this is not 0, and we favorize scanting of the moment at low temperature. So MnSi, why it is interested? Why we got interested in MnSi? So first, because I had a very good friend at the Kurchatov Institute who had strange ideas, but also because it is a non-centrosymmetric system. So it is a homochiral spin spiral, so it turns only in one direction, the magnetic structure, very long wavelengths. You can destroy this magnetic field with a very low pressure, 1.5 GPa. And there is no superconductivity, as we will see when we apply pressure. And you can also destroy this state by applying a very low field. And also in this system, there are the first observation of skyrmions. Tom Lancaster has worked also on this. So 2 words about chirality. So what does it mean? So a chiral object. So if you have an object, you go into a mirror and you have the mirror image. If you cannot superpose the 2 images, this is a chiral object. So for example, your left hand, and your right hand. So, but you have also achiral object, where you can superpose the two objects, the mirror objects and the original object. And I looked for example in the internet, and the one that I found is this. And the mirror image of this is to be from the Back to the Future, and you can superpose the two objects. Eric, you don't tell that to my. So, Muon site determination. Okay, this is my talk of Monday. So, we remember we use the night shift, or the difference between the internal field and the external field. Remember, it was something like that. And what interested us is this dipolar tensor. And so in MnSi, there are actually only two types of sites. No other type of site. There is one site with a multiplicity of 4, which is this guy here, and another one, if you take x, y, z different, has a multiplicity of 12. And manganese and silicon are in the 4a site. And so we thought, okay, maybe the muon is also in the 4a site. And if we assume that the muon is in the 4a site, so there are 4 sites which are crystallographically equivalent, magnetically inequivalent, or they can be inequivalent. So we can calculate the dipolar tensor. So there is always the same constant which comes into play. And now we can think. So if we apply the field in a direction, so whatever direction, what we normally expect to see is 4 different signals. And this is, for example, what we have here. We did an angular scan, and you see we have 4 nice signals. If you apply along 1, 1, 1, you will have a splitting. So 3 of your sites will give you the same response, and 1 will give you another response. And this is what is observed here. You see here, this is an amplitude 3. The ratio is almost 3 here between this guy and this guy, which corresponds to this and this. And if you apply finally along the 1, 0, 0, or the 0, 1, 0, or 0, 0, 1 direction, the dipolar field will be 0, and this is what you observe here. So this is 7.5 Tesla. So basically this reproduces this along 1, 1, 1, and when you go along 1, 0, 0, you have only 1 signal. Maybe you can see here that we have measured 7.5 Tesla. So we take the geomagnetic ratio of the muon, and it should give us a line somewhere here. So why do we have this shift between this line and this line if the dipolar field is 0? We have that because we have demagnetization factor, so demagnetization field, Lorentz field, and the contact term. The contact term is quite important in MnSi. Okay, so we know where the muon is going. It is going on this side, so we compare the dipolar field that we have calculated with the one that we have measured. And if we do a rotation around this angle, why around this angle? Because this axis, because it happened that we had a cylinder like this. And actually, when we did the measurement, we didn't know the orientation of the cylinder. So this is what I expect, and this is what I measure. And you see the agreement is perfect. So we are sure that the muon is here. So now if I apply along 1, 1, 1 direction, I told you 2 signals with ratio of 3, but I can calculate what is the value of the splitting here. You see I write a little bit, here I have to be, okay, one step further. So now what I can do is that I can do measurements at different temperature, different field, and I can plot the splitting here as a function of the magnetization. And I do that as a function of the magnetization because I do have very high field up to 7.5 Tesla. And so if you plot the magnetization as a function of field, for example, Px, it will be linear at the beginning. So this is when the susceptibility comes into play, but at some point you will have some saturation. And so we don't use the moment, but we use the moment with the susceptibility because it's this regime here, but for some points we are out of this linear regime, so we use the magnetization in the formula. So you see we have a perfect agreement. The line is what we expect for this site. We can divide it by 10, still a very good agreement. Divided by 10, still a very good agreement. And this very good agreement that we have between what we measure, the magnetization, if you want, that we measure, and the bulk magnetization tells you that the muon is not perturbating the lattice in this case. Okay. So we have this site here, and at this point we asked Roberto and Pietro Bonfa to do DFT calculation. It was really at the beginning of the DFT calculation. And Pietro and Roberto told me, don't tell me the site. We don't want to be biased, and so we didn't tell them the site. So what I call a blind modus ab initio DFT calculation, and this is what they observed. So they calculate, so it was a perfect agreement with our site. And this was really the start of all this DFT business that we have in MnSi. So we know the muon site. So what can we say about the magnetic structure? So the magnetic structure is helical, as I said, incommensurate. So this is the 111 axis, and your turning of your moment if you go along the 111 axis, very long wavelengths and very small moment. So now you can see what you can calculate what you expect for the sites, and there was a nice example yesterday in the workshop of Francis about that. So you expect the over-Hauser field distribution for 3 of these sites, this one, and this one. But for this one here, if you go along the helix, it will always see the same field. So what you expect, so now you can calculate this value here, this value here, this value here, because you write that the muon field, the field, the muon site will be a dipolar field that you can calculate if you know the magnetic structure, and a contact field, and the contact constant you take what we extracted from the transversal field experiment. So there is no free parameter. So this is what we expect. I put a little bit of broadening as in the experiment, and this is what I measure. You see the agreement is perfect. And this is in the Fourier space, and this is frequency space, and this is time space. So what I can do a little bit further with that. So Pierre Dalmas goes quite a long way with this. We can also, yesterday in the workshop, it was nicely shown that the position of this peak compared to the Oberhauser distribution tell us if we have a left-handed helix or a right-handed helix. So it's quite precise. So we know that we have a left-handed helix here, and after you can go ahead and play a little bit. There are 2 Bikov orbit. I don't want to go too much into the details. And you can say something how your helix is turning if you go along the 111 axis. It is turning smoothly, or is there steps from time to time? And between the 2 helix, there is actually a phase. It was found that it is -2 degrees. And this kind of stuff you can measure by playing yourself. So here there is a nice article by Pierre. So he discussed about all the details that you can extract from MnSi. And you see we are extremely sensitive to the magnetic moment. You see, if we have a small change of 10% for the magnetic moment, this will give us a completely different Oberhauser field distribution. So we can precisely give the value of the ordered moment. This is the phase that I was speaking about, that from time to time you have a phase slip, and we can also determine that we have this kind of phase slip, and this is the K vector. Okay. So now, we thought about that to apply pressure in MnSi, because it's let's say a strongly correlated electron system, and normally in this system you have an order, magnetic order, and when you apply pressure, you go to a quantum critical point, and around this quantum critical point, you have sometimes quite interesting phenomena. And we wanted to see if there is something like that in MnSi. So these were measurements that we did with Anveika. So this is the reason why we develop also this pressure cell with Daniel, that point. So, and you see that when we are just below the quantum critical point, we still have oscillation. And when we go above the critical point, we have only relaxation and we lose the frequency. This is the magnetic volume. We can very nicely also find the magnetic volume. There is no phase separation, the opposite of what Tomo Uemura was saying. And we can look at the critical temperature as a function of pressure and so on. So everything is fine, but we didn't find any superconducting phase on PC. And this is what we wanted actually to see. So what is the reason for that? And probably the reason lies in the so-called Anderson's theorem. So to form a Cooper pair, there are actually two symmetry which are important. One is the time reversal symmetry, and the other one is the inversion symmetry. The time reversal symmetry is important if you have S wave or P wave superconductor. It's always there. So for example, if you have S wave, to form your Cooper pair, you need this state and this state. And you can have this state only if you have time reversal symmetry operation on this one. Otherwise, this will not work. Now for the spin triplet, you want, for example, up is a k total equal to 0, so you need this state and this state here. And you can reach this state from here only if you have this, this inversion symmetry. Okay? And in MnSi, we don't have this inversion symmetry. So what does it mean? That if you don't have this inversion symmetry here, this triplet state will be not possible. On MnSi, so the order locally is almost ferromagnetic because the wavelength is so long. So what we expect to see at the quantum critical point, we expect to have almost ferromagnetic fluctuations. And if these fluctuations actually would promote superconductivity, they would promote the superconductivity in a P-wave state. But since we don't have this inversion symmetry in MnSi, most probably this is the reason why we don't have superconductivity in this system. Okay, I come already at the end of my talk. Told you the muon side determination. Once you know that, you can say a lot of this muon. If you know exactly where the muon is going, we have seen MnSi under pressure. We have seen that, for example, there is no superconducting state. I didn't speak about that because I said I didn't have time. So there is a skyrmion in MnSi, skyrmion phase. So there are some works done by Tom Lancaster. We did also some work which are still not published. I would like to publish them, but other people would like to wait a bit. And it seems that we are seeing this skyrmion state also with me. Okay, this is what I want to say.
Questions, Alex? Anybody? Anybody? I was just wondering, just considering we're in a workshop in school, new users of muons potentially. If you could consider this case study and talk to your 21-year-old self about this work, what would you advise yourself to do in terms of experiment, theory, collaboration?
So what I would do is first to start an experiment, only if you have a good crystal. Because sometimes you begin, you do not have a good crystal, but you want to give it a shot, and it can be very bad. So, okay, also Heidi told us that it is good to look at the samples before to put them in the MnSi beamline, and I think this is really important. So go to a MnSi beamline once you have a very good sample. If you have a single crystal, it's even better. And collaborate with very good people, so they are knowing what they are, they know what they are doing. So.
No, thank you, Alex. Any question?
I have a comment. Alex is too kind. No, but just two small comments. One is that the DFT study can also predict the hyperfine coupling.
Yes.
Cannot compete with the precision of Alex measurement, but to within 10%. It's the same value.
The same value.
Yeah. So and it's been published. So it is, and it profits from calculating this hyperfine value, including a muon light particle, a quantum effect. It doesn't improve very much if you do that in a rough way or in a better way. That's also a message. Now the other thing,
you don't need a superlative. So what?
You could try and overcome the problem that you're not treating on equal pairs the electron wave function in DFT and the muon. You're always doing the muon quantum effect separately afterwards, and in reality they are on the same part. So if you try to do it better in this case, you don't get a great improvement. And the last comment is that you said incidentally that in order to have Jaruzelski-Mourier, you have to have a non-cytosymmetric system. You have Jaruzelski-Mourier in reality also in on single atoms in a centrosymmetric system.
You have also locally non-centrosymmetric.
It means that you don't get a helix, but you simply get canting.
Exactly. Yes, you're perfect.
Thank you. Yeah. Oh, well, questions. Hola.
So why were you expecting superconductivity under pressure in this system?
Because a lot of this system, at least a strongly correlated system, when you, it was not particularly superconductivity, but when you come around the quantum critical point, you have always very strange non-Fermi liquid behavior or superconductivity or something like that. So we were hoping that we would see something.
Manganese phosphide, right?
Yeah.
Manganese phosphide growing arsenide also critical, superconductive.
Steve,
yeah, before your studies, there were these older measurements by Yamura's group looking at manganese silicide. I think they were mainly looking in the paramagnetic state. Now you know so much more about the site and what's going on in manganese silicide. Is there anything one can infer about those older measurements?
Yeah, no, they did also measurements in magnetic state. And, so you remember the field distribution, so it's a delta function and this overall field distribution, and basically they fitted that. They were thinking there were only two peaks, and they were fitting two frequencies. And another thing that we can learn is sometimes it's good to do very long experiments at one temperature to have a very good field distribution. Because this is something, if you don't do a very long measurement, you will not see that.
But they were also looking in the paramagnetic state, weren't they, above the transition and looking at the relaxation.
Yeah, they were looking also at the diffusion of the muons.
Yes.
So, but these are perfectly good results.
Okay, thank you. Let's thank Alex again.